Now, ladies and gentlemen, it's time to tie electrochemistry into, that's right, thermodynamics. So remember, thermodynamics talks about the direction that a reaction moves. So if A is turning into B, if this reaction is spontaneous, that means yes, A will turn into B. If it's not spontaneous, as written, that typically means what's going to happen is B is actually more likely to turn into A. And so while this reaction right here might not be thermodynamically favorable or spontaneous, this reaction might very well be. And so in the case of thermodynamics we talked about before, the delta G for this reaction, if it is non-spontaneous, is going to be greater than 0, whereas this reaction, if it is spontaneous, delta G will be less than 0. So a positive delta G means a non-spontaneous reaction, whereas a negative delta G means a spontaneous reaction. And redox reactions are no exception. So for example, this reaction right here, Zn2+ turning into silver, we can see this reaction shows silver giving 2 electrons to zinc, so zinc in this case is being reduced. This right here is a non-spontaneous reaction. In other words, this reaction would not occur. The delta G is going to be greater than 0, which means the reaction is non-spontaneous as written. But if it's not spontaneous in this direction, with a redox reaction, it means it is spontaneous in this direction. So if we just write it like this, now the delta G is going to be less than 0 and it becomes a spontaneous reaction. So if we were to combine all 4 of these things right here, it's not like no reaction would occur, it would just occur backwards. So the zinc and the silver ions are going to change into that right there. But we don't always need delta G to tell us whether or not a reaction is spontaneous. We can use the E of the cell when it comes to redox reactions. So if the E of the cell is a positive number, that means it is a thermodynamically favored reaction. But if the E of the cell is less than 0, so we get a negative voltage, that means it's not thermodynamically favored as written. But if we flip the reaction, we would get a positive voltage, and we would have a thermodynamically favored reaction. So anytime you get a negative voltage, reaction is occurring, it's just happening backwards from what you expected it to be. Flip the reaction, it becomes positive, there you go. Oh, hey, here's an example. So barium sulfate reacting with lead solid, and so the barium sulfate is our aqueous and the lead sulfate. If we take our spectators out of here, this would be barium 2+, and this would be lead 2+. So sulfate's just a spectator ion. So in this particular reaction right here, we see barium 2+ is turning into barium solid. So it's written like this, showing barium being reduced. So that means that this value right here can stay as written. And then we have lead turning from lead solid into lead 2+, which is backwards from what we have right here. So we need to flip that reaction and then flip the sign of this guy. So when we flip the reaction, flip the sign so it matches what's written up here, we wind up with the E of the cell being a negative 2.77. So this means the reaction is non-spontaneous as written. So electrons are flowing. We know electrons are flowing because we get a voltage, but they're not flowing from lead to barium like it shows in this reaction. Instead, they're flowing from barium to lead, producing this as our products, and these are our reactants. So if we flip the reaction, we would have this right here, and we know that this one is spontaneous, and the E of this cell would just be a positive 2.77 volts.